So let us start, friends.
Today is it just the online class or what?
Sorry.
No, there's a WhatsApp from. Oh, okay, no, it's he's saying that there will be no classroom today. It's just the online one.
Yeah, that's we already communicated, right?
I don't know. They have started.
Anybody is there from the classroom?
It is online. The class is started. It just started.
No. Anybody has actually traveled? So anybody is attending from XLR? Okay, fine, no problem. Let's start there. Okay. So friends, today we are going to discuss about, we'll be starting with the machine learning. Okay. The broad level categorization or classification we already looked at in last session, wherein as part of data mining, we'll have supervised learning or machine learning and unsupervised learning. When you know the output variable which you are predicting, then we go for machine learning algorithms. And if you don't know what is the output variable that you are predicting, then you go for unsupervised learning. And today we are starting with the first algorithm as part of machine learning, which is linear regression. We have already discussed the scatter plot, right, in last session. Am I right, friends? Did we discuss about the scatter plot? The correlation. Guys, please, can you confirm? Did we discuss or no? Nobody remember? Praveen, Hanika, Anil. Okay, fine. Let me do a quick recap. Doesn't really matter. So scatter plot tells us three things. One is the direction of the data. Is it positive or is it negative? And there is no relationship. The direction of the relationship. Scatter plot talks about the relationship and its direction and the strength of it. Strength means if the scatterness between the data points is too less, that means they're tightly coupled, like what you're seeing here. That means it's a positive, it's a perfect or more strong relationship. And the data spread like this, the spread is more. That means it's a moderate relationship between the two variables. If you're saying the data has been spread like this, there is no direction, there is no clear indication of how a variable is maintaining a relationship with the other variables, then call that as no relationship. The direction could be positive or negative, and the strength of the relationship. By looking at the scatter diagram, it's very difficult to actually comment anything about the strength of the relationship. To bring the objectivity, that's where we go for correlation coefficient. Correlation coefficient gives an objective indication in terms of how strongly or how two variables are related. When the correlation coefficient R, if the mod of R, because the range of the values it takes is -1 to +1. If mod of R, modulus of R is greater than 0.85, then you call that as a very strong relationship. The reason why we are taking mod, what happens if I apply mod to any value? Friends?
Gets positive.
Yeah, it becomes positive. Even the negative values will be converted to positives, right? When the strength of the relationship is greater than 0.85, the mod of R, then you call that as a strong relationship. If it is between 0.5 and 0.85, then you call that as moderate correlation, moderate relationship. If it is less than 0.5, then call that as a weak relationship. Okay. Correlation coefficient is represented by small r. It takes the values between the range of -1 to +1. If the r value is +1, that means that is a perfect positive relationship. That means one variable, the variable x, is maintaining a perfect positive relationship with y. It looks like a line, positive. As there is an unit increase in the value of x, the relevant increase that you are observing over the y as well. That's why it is called as perfect positive relationship. But at the same time, if there is a unit increase in x, to the same extent, if y is decreasing rather increasing, that's called perfect negative relationship. It looks like this. When x value is small, you have the y value as the highest one. When x is more, it keeps increasing and reaches to the more value, then the y value drops off. It's called perfect negative relationship. So when r, small r, is -1, that's when the graph looks like this. The scatter diagram between the two variables looks like this. Can you give me an example for perfect positive relationship? Guys? Yeah, that's perfectly fine, Praveen. I've been covering already. I'm covering this. This is the only starting part before we discuss with the linear regression, which is the first algorithm of machine learning.
Okay. Thank you.
Yeah. So when there is a unit increase in x, you're observing a relative increase in y. Same amount of increase in y. Then you call that as a perfect positive relationship. Can you give me an example where when x value is increasing, your y value is also increasing? When the cost of advertisement that you are spending, your advertisement spent, the amount that you are spending towards advertisement, if it is fetching the sales, if it is helping in increasing the sales, then Your X could be the advertisement cost, and Y variable could be the sales, increase in sales or the sales. So that you can see as the cost of your advertisement is increasing, your sale value is also increasing. And similarly, can you give me an example this for the perfect negative relationship? Guys, anybody is having challenges with the internet? Seeing people are dropping off and joining back.
Everything is good.
Sorry?
Everything is good, Ramakrishna.
Okay. Yeah. Somebody joined with the name XLR. Who is that man? Okay, fine. So can you give me an example where when X is increasing, the Y is decreasing? Perfect negative relationship.
When price increases, consumption decreases.
Right, exactly. When price of a product is increasing, the consumption rate obviously comes down. You'll have very less takers when price is increasing for a product, right? But at the same time, at the first place, why do we need to look at the relationship between two variables? Right? So far, whatever we discussed helps you as part of EDA, exploratory data analysis. So far, whatever we discussed, what exactly we do in exploratory data analysis, friends? First, you understand the business problem, then you collect the data and start cleansing the data. Once you are done with the cleansing of data cleansing, that's when you start with EDA. So the EDA, you perform univariate analysis, bivariate analysis, and multivariate analysis. So what exactly you perform as part of univariate analysis? As the name suggests, we take each of the variable at a time, single variable, univariate, single variable at a time, and understand what kind of analysis, preliminary analysis we can perform on a univariate or the single variable, friends. What all we can do? If I take a single variable, what all insights or what all I can understand about the data of that particular single variable? Guys, please respond. What all I can do? Okay, which variable has more influence? Unit of each variance. Very okay. So all the topics whatever we discussed so far, measures of central tendency, measures of variance, skewness, kurtosis, box plot, okay, and the distribution of the data, all these things can be performed on a univariate space. You can take each variable as a standalone and see how all these values look like, what is the shape of the data through the histograms, and how the data is distributed. Is it normally distributed or not normally distributed? How your basic statistics looks like, the mean, median, mode, variance, range. Yeah. And if you have any outliers existing in your data. Clear? So these are all what we can perform at the univariate level. But what is bivariate? What kind of insights we can understand by taking two variables together? That's what we have just discussed, the correlation, the relationship between two variables. Whenever you are going for prediction of a variable y, to make sure it maintains a good relationship with all input variables. Okay, it maintains a good relationship with all input variables. So y towards x1, y towards x2, and so on. And what is multivariate analysis? That's what we're going to see when we discuss about the modeling with the linear regression and further algorithms. Am I clear, friends? Any questions so far?
No.
So are we clear what exactly we do as part of EDA, exploratory data analysis? Believe me, friends, like data collection, cleansing, EDA, all this work is going to take about 60 to 70% of your project time. This is where most of the time you are going to spend. Okay, hence make sure you get it right. Okay. Now, to understand how a variable, a change in a variable is influencing the moment of the variable 2. How a change in a value of variable 1 is influencing the variable 2 is what we are going to understand through scatter diagrams. As part of scatter diagram, there are 3 combinations that you would need to look at based on type of the data. One is continuous to continuous. You always get to, if your y variable is continuous, then you get to see continuous to continuous as a pair, y versus x. Y is nothing but output variable, x is nothing but input variable. And what is the other combination? Y being continuous, x being discrete, right? And y being discrete, x being continuous, y being discrete, x being discrete as well. So these are 4 combinations that you're going to look at from the relationship perspective between 2 variables. But is it always we need to see the relationship between every variable with the output variable? Why? We also need to check the relationship between two input variables, x1 and x2, x2, x3, and so on. What kind of insights that we can bring out by looking at the relationship between two input variables, we will see in a while. Okay. The movement of value x and the respective movement of y as per change that is happening in x is what is going to determine the relationship between the two variables. In order to bring the objectivity, I might feel this is perfect positive correlation, but some of you might feel they're not exactly on the line. Okay, to remove that confusion, we bring the objectivity by looking at the measure called correlation coefficient. Correlation coefficient, small r. To look at the correlation coefficient to understand the strength of the relationship. It also tells us the direction of the relationship by using plus or minus sign, right? The range of values that this correlation coefficient takes is basically -1 to +1, where -1 being perfect negative correlation, +1 being perfect positive correlation. And if there is no relationship between two variables at all, the correlation coefficient value will be 0. And as we discussed, if the modulus of R is greater than 0.85, then you can call that there is a strong relationship existing between two variables. If it is between 0.5 and 0.85, then you can call that as a moderate relationship. If it is less than 0.5, then you can call that as a very weak relationship. 0 being no relationship, +1 being perfect positive relationship, and -1 is perfect negative correlation. Are we clear, friends? Any questions before I move forward? Okay. So this is a perfect positive correlation. This is a negative correlation. And if you see the correlation is parallel to your x-axis, that means there is no correlation. Irrespective of the movement of values in x, there is no change in a y value. That's the reason you are seeing the relationship is very parallel to the x-axis. So this is a mathematical formula, friends, but you don't need to remember this. Just for your information. Basically, we make use of these statistical tools, R and Python, to calculate all this. Okay, don't worry about that. Any questions, friends, before I move on to the machine learning algorithm, the first machine learning algorithm, which is linear regression. Just give me a second, friends. Sorry, guys. Sorry about that. Okay, let's start with the first machine learning algorithm, which is linear regression. Even before getting into linear regression, let's try to recollect from our academics. What is this, friends? Guys, anybody remember what is this? Function of x, right? Y is equal to function of x. That means, so the y is called as the dependent variable. Dependent variable or the output variable. As somebody's webcam is on, okay, yeah. Dependent variable. The value of y is dependent on the function that you apply on the value of x. Hence, y is called as dependent variable and x is called as independent variable. So y is called as the output variable or the dependent variable, whereas x is called as the input variable or independent variable. The value of y is dependent on the function that you apply on the value of x. That's why x is independent variable and y is the dependent variable or the output variable. What is the straight line equation, friends? What is the straight line equation? Y is equal to mx plus c. Yeah, that's right, Hanika. Y is equal to mx plus c. So we already know that y is the output variable or dependent variable. X is the input variable or independent variable. What is c in this?
Constant.
Constant. Are you sure? But what exactly this constant means? How do you represent that on a two-dimensional graph? Let us say, yeah, this is x-axis and this is y-axis. So how do you represent this straight line y is equal to mx plus c? And where exactly the c comes? Let us say the straight line that you have drawn is this, y is equal to mx plus c. Where do you think the c will be like?
Gap,
Sorry?
the gap between that line and the base horizontal line. C.
Oh, you're talking about this region?
Right.
No. C is nothing but the intercept value. Intercept is nothing but the point at which your straight line y is equal to mx plus c interacts with the y-axis. That is nothing but your c. Clear? And what is m here in this? What is m here?
Slope.
Slope, right? What is slope? This is a straight line. We are dealing with a straight line. If we take any 2 points, any 2 consecutive points on that straight line, and if we calculate the slope, how do you calculate the slope? Through Pythagoras theorem, right angle triangle, right? Through this, you can identify what is the slope of it. But if I have 2 data points, how do I represent a point on a 2-dimensional space? Guys, how do we represent a point on a 2-dimensional space graphically? Using what coordinates?
X and Y.
X coordinate and Y coordinate. Like to represent that, x1 comma y1, x2 comma y2. Right? Now, if I want to calculate the slope between these two, anybody remember the formula that we used to calculate the slope?
Y2 minus Y1 divided by X2 minus X1.
Exactly. y2 minus y1 divided by x2 minus x1. Clear? So now, using this right angle triangle, Pythagoras theorem, then you can calculate the slope between the two. So what is the slope? This is a slope between to what extent your x is influencing y is what the slope is going to tell us. In other words, this m is also called as the coefficient of x. Right? Are we clear about this, friends? Any questions you can ask me. You should get this right. Otherwise, you will not understand. You will not be able to understand the linear regression. Any questions you can ask me. Any slightest doubt also you can ask. It's not something we are learning newly, right? We just recollected what we learned in our school days. That's it. Clear? So now, in the same line, linear regression, as the name suggests, here we are trying to identify the line, but we will write this little differently compared to the straight line. The straight line equation is y is equal to mx plus c. But here we will write that as y is equal to beta naught plus beta 1 x plus epsilon. What are these beta naught and beta 1 x?
Okay.
Coefficients, right? But this beta naught is called as the intercept value, whereas beta 1 is the coefficient of x. And what is this epsilon, friends? What is this epsilon? Epsilon is nothing but the error. See, we are predicting a value. We are predicting the value of y based on the intercept coefficient of x and x value. So can a prediction be 100% accurate? Is it possible? Guys, come on.
No.
All right. Obviously, your predictions tend to deviate from the actuals. In order to fill that gap, the difference of your predictions towards the actual, this beta naught plus beta 1 x will be used to predict a value. If you are predicting a value of y, then you represent that as y cap. Y cap is nothing but the predicted value. The difference between y and y cap is nothing but the error that you are making with your prediction. So to calculate the error, the formula will be y minus y cap. Actual value minus predicted value. Clear? So the line which we are drawing, the beta naught plus beta 1 x, is also a straight line, but the intercept at which your line touches the y axis, that is called y intercept, which is nothing but beta naught. And beta 1 is the coefficient. Beta 1 is the coefficient of x. And y is the output variable and x is the independent variable or input variable. Okay. So that's what we are discussing here. and y is equal to beta naught plus beta 1x. Both these beta naught and beta 1 are called as parameters or coefficients. They're also called as parameters. And epsilon is the error term. So through the equation of this straight line, y is equal to beta naught plus beta 1x plus epsilon. So now we are trying to understand the relationship between how this independent variable x is related to the output variable or the dependent variable y. And to calculate beta naught and beta 1, these are the mathematical formulas that will be used internally. Of course, we don't need to remember these formulas. Just remember this one. Pay attention, my friends. It's very important. When the equation that you're using, straight line equation, y is equal to beta naught plus beta 1 x. But how this line will be drawn? So when you are drawing the relationship between the scatter plot between x and y, you will see the data points like this, various data points. They're spread across the two-dimensional space. But is this only straight line that is possible to be drawn that goes through these data points? Is this the only line that we can draw, friends, that goes through these data points? How many lines we can draw? Guys, please respond. Now it's post lunch. It's a little difficult for you first to be active. Well, otherwise, there's no point in going through. So how many lines we can draw from these data points? Like the line that you're seeing that y is equal to beta naught plus beta 1x. Am I audible? Are you able to hear me?
Yeah.
Okay. So can I draw a line like this? 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 Similarly, how many lines I can draw that goes through these data points? Multiple lines, infinite lines. We can draw n number of lines, right? But out of all these lines, how do we choose only one line that we can make use of for our prediction? It is nothing but this y is equal to beta naught plus beta 1x. When we are predicting y, that is y hat, We know what are the x values. We are already given the x values. Only then we go for predicting the y value. When we are predicting this y, the values of these coefficients, beta naught plus beta 1, are going to influence the output variable to the maximum. So out of all these lines, what is our ultimate objective, friends? What is our ultimate objective when we are deriving this line y is equal to beta naught plus beta 1x? Guys, anybody? What is our ultimate objective to derive this line y is equal to beta naught plus beta 1x?
To know what about how far is our predicted values from the actual.
Okay. So our objective is to understand how far is our predicted values from the actuals. Or can I frame the same statement like this? So my objective of determining this y is equal to beta naught plus beta 1x is nothing but to come out a line which has got the least error possible compared to the other lines. Can I say it like that? So whatever the line that I'm going to use, based on that, I'm going to predict the value of y. Am I making sense, friends? So the y-intercept value and the coefficient of x are going to help me to predict the value of y at a given value of x. And the same thing is represented the fitting values, fitted values. Fitted values are the x predicted values, both are same. Fitted values are expected values. The fitted values, the predicted values of y is represented as y hat is equal to beta naught predicted value of beta naught plus predicted value of beta 1 into x. So how this line we are finalizing, how this line will be selected out of all these n number of lines. We select this line, we take this line as a finalized one. Depends on whichever the line has got the least distance with all the data points. That line will be selected as the best fit line. This line, whichever is selected, this is called as best fit line. Okay. But how do we determine that the line that we are selecting as the best fit line has maintained the least distance with all the data points? How do we calculate the distance, friends? How do we calculate the distance between two data points? Let's say we have x1, y1, and x2, y2. How do we calculate the distance between these two data points? What is the formula, friends? Distance d equal to yes, anybody remember?
Pythagoras theorem.
What is the formula?
Under root y2 square minus y1 square.
Oh, is that is the slope, right? But here we are talking about the distance. Formula to calculate the distance is square root of x2 minus x1 whole square plus y2 minus y1 whole square. Why are we sparing it and then taking a square root? We are saying, how do we represent the data point in a two-dimensional space? Let us say this is x. Say this is 1, 2, 3. And this is also 1, 2, 3. So if I have a data point called 2, 3, where will it come, friends? How can I represent the 2, 3 in this graph? So 2 is of which coordinate?
X.
X. X, I take 2. And Y, we have 3. So it will be here. And this is the data point that's represented as 2.2, 3. Clear? And similarly, if I take the distance, another data point as 3, 1, that will be like this. So if I apply the distance formula on these two data points, 2, 3 and 3, 1, if I take x2 minus x1, this is x1, y1, and this is x2, y2. Right? When I apply this formula, so what's the value that you're going to get? Square root of, what is x2, friends?
3.
3 minus x1,
2.
2 whole square plus y2 minus y1 whole square. 1 minus
3.
3 whole square. So if you look at this part, your y1 value is greater than y2 value. 1 minus 3, if you solve, how much do you get? Minus 2, right? Can a distance be negative between two data points? Can a distance be negative ever? It should always be positive. It cannot be negative. And that's the whole reason the formula has been introduced as square root of x2 minus x1 whole square. Even though your underlying result of this expression is minus, by squaring it, it will be converted to positives. 3 minus 2 whole square, that is 1 square. 1 plus minus 2 whole square, which is 4. Right? So overall, you will get just a second, friends. Overall, you will get square root of 5. Am I clear now? Now, why are we talking about this distance now? Now, the line which maintains the least distance with all the data points. How do I calculate the distance of a data point to the line? Nothing but we draw the orthogonal line from a data point onto the line that we are calculating the distance for. We calculate this distance for all the data points with all the lines. Whichever the line has got the least distance will be selected as the best fit line. So the technique of selecting the best fit line based on the least distance is called as ordinary least square technique, OLS. Okay. Now, the difference of your actuals and the predicted. Actuals are the data points what you are seeing. Predicted values are nothing but the relevant data points on the line. Because line is the one you are based on which you are predicting. Line is the equation based on which you are predicting the output variables, output values. Right? The difference of the actual values and the predicted values which are there in the line is nothing but, let's say, if this is the relevant data point on the line for this, now the distance, the difference of these two is nothing but the error that I am making towards my prediction. Am I clear with this slide, friends? The technique based on which the best fit line is selected is OLS, ordinary least square technique. Okay. Let's move forward. Okay. Now the regression is all about the regression equation y is equal to beta naught plus beta 1 x. right? Guys, let's take a quick 5 minutes break and come back. Is that fine, guys?
Yeah.
Okay. Okay, guys, are you back?
Yeah.
Okay. But how do we determine the effectiveness of the line that you are coming out for your predictions? So this is the equation that you're going to rely upon to predict the y value based on the intercept value, beta 1 coefficient, and x value. How do you know that the effectiveness of that equation or the line that you are finalizing based on OLS technique? That's where in both R and Python, you can make use of this measure called R squared value. This R squared value tells you in terms of how many data points, how many actual data points are actually falling on the line that you are drawing as a best fit line. Means the percentage of the data points being covered are being existing on the line that you are coming out with. Means if the data points are actually lying on the exactly on the line, that means your prediction is in line with the actual. Am I correct? So there is no deviation. If the data point, original actual data point lying on this line, which are coming out for prediction, that means there is no deviation from the actuals. The predicted values are same as your actual values. So the R squared value tells us how much percentage of this data is lying exactly on the line. That's what this R squared value tells. How much of the percentage of your predictions are effective towards the actual data. So this works in terms of understanding the accuracy of the model that you are building, the linear regression model. The R squared value is always between 0 and 1. 0 and 1 or 0 and 100%. If the R squared value is more than 0.8, then you can call that as a very strong correlation. What do we mean by correlation? Why are we talking about correlation here? Though we are talking about R squared value, where the small r talks about the correlation coefficient, where the R squared value talks about coefficient of determination. Terminologies are very important, friends. The small r is called as correlation coefficient. It talks about the relationship between two variables. And whereas the capital R squared value is called as coefficient of determination. It's called as coefficient of determination. It takes the values between 0 and 1 or 0 and 100%. If the value is more than 0.8, then you call that as a very strong relationship, very strong correlation. That means your X values are helping the Y value to this level of accuracy. If the R squared value is between 0.65 and 0.8, then you call that as a moderate correlation. If it is below 0.65, then you call that as a weak correlation. We will see how do we interpret these R squared values and all these things. Okay. But let's try to understand how this R squared value will be calculated. This SSR is nothing but sum of squared residuals. What is a residual? Residual is nothing but the difference of the predicted values y cap minus the average of that value, which is nothing but y bar. The summation of the difference of each of the variable from its average mean whole square. Means what are we capturing here, friends? What are we capturing? The difference of predicted values towards the mean of it. What are we capturing? It's not about error, it's about the variance that we are capturing. If you look, remember the variance formula. Summation of x minus mu whole square divided by n, right? So the deviation of each of the predicted value or the difference between each of the predicted value towards its mean is the explained variance that is being captured by sum of squared residuals. Now, the difference between actual values and predicted values is being calculated by sum of squared errors. Error is unexplained variance. This explained variance is by through the model what you are using, to what level of accuracy you are predicting is what is being this variance will tell us. Unexplained variance is how far you are going wrong. Now, sum of these two, sum of squared residuals and sum of squared error, is what? How far is your actual data is deviating from the difference between the actual data and the mean value of it. Now, to calculate R squared value, the formula is SSR, sum of squared residuals, divided by sum of squared total. That's why it lies in the range of 0 to 1. Am I clear, folks? Okay. Okay, pay attention, friends. So what is the confidence interval formula, friends? How do we calculate the confidence interval? CI equal to what is confidence interval formula?
X bar plus or minus.
Is x bar, right? Not x square. To predict confidence interval, we baseline the mean value, which is x bar, as a point estimate, plus or minus the margin
Z1
of,
minus alpha.
the margin of error, which is nothing but z at 1 minus alpha. 1 minus alpha being the confidence level, z at 1 minus alpha into standard error, which is sigma by root 10. Am I correct? Now,
Yes.
so that means we are baselining the mean as a measure to come out with the confidence interval by how much we could deviate on both the sides of this mean value with our prediction. And that's what the confidence interval talks about. But if we take the prediction interval, It's again a range in which your predictors or the new value that you're coming out or you're predicting would fall in that range, in that specified range. Now, based on this, can you tell me whether the prediction interval range or confidence interval range, which one is more, which one is less? Your prediction interval range would be more, or confidence interval range would be. Which one do you think is more fair? Because ultimately our confidence interval would be more or less very close to your mean value, confidence interval. Whereas your prediction interval, because you are not going with any confidence level, right? Your obviously your prediction interval is much more compared to the confidence interval. That's why your prediction interval is always wider than the confidence interval. Because of the uncertainty that is involved in predicting for the new value, right? But whereas in case of confidence interval, you are baselining around the mean value. And you are actually trying to come out with what is the margin of error you could go on either side of this mean value, right? Hence, always whenever we are coming out with a prediction, it is not suggested to predict a single continuous output value. So whenever the y variable is continuous, whenever the y variable, the output variable that you are predicting is continuous, that's when you go for the linear regression. So when y is continuous, so what is the probability associated in predicting a single continuous output value?
Zero.
Zero, right? That is the whole reason we need to predict a range of values rather going with the single value predictions. And that's why we are discussing about prediction interval and confidence interval. Clear? Guys, anybody has got the network issues? People are dropping off and coming back. Okay. So as I told, when y is continuous, that's when we go for linear regression. But at the same time, we also need to see when y is continuous and x is single variable and x is also a continuous variable, then also we go for simple linear regression. Simple in the sense because the number of input variables that you're using is just one single variable. That's why it is called a simple linear regression. When y is continuous and x is single, but x is discrete this time. What are discrete, friends?
0 or 1. Otherwise, categorical.
Discrete is nothing but the categorical, right? Classes, 2 class, 3 class, right? Even then, we can go for simple linear regression. So that means irrespective of the type of your input variable, whether it is continuous or discrete, you're going for the simple linear regression when the y variable which you are predicting is continuous. But when your x variable is discrete, what is discrete, friends? Let us say x variable is gender. This is male, female, are the possible values. Okay. If I just produce the same text, if I just give the same variable as a text variable to the algorithm, would it be able to understand anything? Would the machine be able to understand anything of this text data? Just any other label data, text data. So it cannot understand. It cannot understand, right? Hence, we need to create the dummy variable. How do we create the dummy variable? Did we already look at this, friends? I think we already seen, right? How do we create the dummy variables? Okay. So how many classes I have for this variable gender? 2 classes, right? So instead of one variable, I would create 2 variables. G underscore M is one variable and G underscore F is another variable. So if the first record has got the value as male, now the dummy variable of male would be marked as 1 and the dummy variable for female would be marked as 0. When the value of the next record is female, the dummy variable of male will be marked as 0 and female record will be marked as 1. But why are we doing all this roundabout way about of work? Why can't we just replace male with 1, female with 0, or vice versa? Why can't we just do that? If I just replace this original values, male, female, with this type of classification, 1 and 0s, dummy variables. What is the disadvantage? Why can't I go ahead with this approach, friends? Or can I go ahead with this approach of just replacing the original value with this sort of data? What is the kind of, can I go with that approach?
Maybe the machine becomes biased to use one and give one.
Yeah, exactly. So what is the linear regression equation? Y is equal to beta naught plus beta 1x. So that means I'm going to replace this x value with 1 for male record, with 0 for female record. If I replace this x value with 0 for female record, so this entire value would become 0. Clear? But in case of a male, I'm replacing that with 1, so that whatever the coefficient value, accordingly, the entire value will be resulted in. That means I'm getting biased towards a class. So for all female records, I'll not be able to, the output variable will always be equal to the intercept value, which is not correct. We're getting biased towards one class. That's the whole reason. Instead of replacing this with the straight numbers, or can I go ahead, instead of ones and zeros, can I go ahead and mark male as 1 and female as 2? Okay, in the earlier approach, we are replacing female records with zeros, which is causing the ignorance of that class completely. Instead of 1 and 0, can I go ahead and replace male with 1, female with 2? You think that's the right approach? All right, here also we're getting biased. So if I replace this gender value, 1 for male and 2 for female, so that means I'm giving more weightage for female records. Right? Hence, and this is the best approach, creating these 2 columns will solve the problem and would not get biased to any of the classes. Would make sure will take care of the balancing of the classes. Right? Hence, you should follow this approach for creating dummy variables whenever you would like to create. Clear? Guys, any questions with this approach? Okay. Hence, you cannot go with this type of dummy variable creation. Now, please can you go through this case study for a couple of minutes? Then we will look at the relevant data and try to build a linear regression model. Please go through it. So done, guys. Have we gone through this? So what is the output variable we are predicting here? So what is the output variable we are predicting? Anybody? Adipose tissue, right? So the adipose tissue is the Y variable that we are predicting here. And what is the X variable? Waist circumference. What is this problem is all about? In order to identify this output variable adipose tissue, there is no other way that you have other than going through the CT scan. But there are some disadvantages going through with CT scan. It's very expensive and it cannot be established in all the hospitals. And it gives a lot of radiation as well. So other than that, if we can come out with a simple model, which is not expensive, which can be easily accessible by all the hospitals, so that will be good. So based on some research, they identified the waist circumference has got the of getting abdominal AT area using simple measurements of the body. So the adipose, the waist circumference is found to be the more having highest influence in terms of predicting this adipose tissue, right? So you need to predict Y using X. For adipose tissue, you need to predict adipose tissue value by using waist circumference, right? Let's look at the data. Only then we can understand which type of the data and which model we need to go for. So these are the waist circumference values. These are the adipose tissue values. So adipose tissue is the Y variable and waist circumference is the X variable. So what is the type of your Y variable, friends? Sorry?
Continuous.
Continuous, right? It is purely in the decimal format. It is continuous. And Y is continuous. And number of input variables is 1. And the type of your input variable is X. Also continuous. Which model do you go for? Which algorithm you can make use of? Simple linear regression. Because you are predicting Y, which is continuous. Number of input variables is 1. That's when you use simple linear regression. Okay, fine. Let's take a break and come back by 4:10, friends. Then we'll resume our discussion. We'll see the model building part. Okay. the recording. Okay, so first I'm loading this data, wc.80, the same data that has got two variables. One is waist circumference, the other one is adipose tissue. So now the data has been successfully loaded. So we have the data of 109 observations, nothing but 109 patients' details, the respective waist circumference and adipose tissue values, two variables. So as part of VDA, we're just looking at summary. What does summary function give, friends? What does it give? What does summary function give in R? Gives us the basic stats information, right? So what is the minimum value? What is the maximum value? Adipose tissue. So what do you think about this data based on this basic stats information? What do you think about the data? To be able to find out any insights? Any wild guess? What do you think about the distribution of the data? By looking at these basic stats, right skewed of which value? Which value is right skewed? Okay, adipose tissue is right skewed because the mean is tends towards the
It should be left to, right?
yeah, it is left skewed. Mean is there, but third quartile is the first quartile. There's too much of gap between first quartile and median. Hence, it is left skewed data. Okay. Okay, fine. So let's first see the dot plot. What does this dot plot give? Waist circumference and adipose tissue. This is a variable name into which the entire data is saved. I'm referring data frame name dollar column waist main equal to, there's a heading that we would like to. So dot plot for X variable. Waist circumference value. If you just look at the dot plot, this is how it looks like. And if you look at the dot plot for Y value, yeah. So they're all basic KDA that you can perform different. Let's see the histogram to understand the shape of the data for waist circumference value. Now, what do you think about the shape of the data? The normal distributed? How the data is distributed, friends? What do you think about the distribution of the data?
Kinda
More towards right skewed, right? Similarly, the y value, histogram of y. More of left skewed data. The tail is towards the right side. Is it positively skewed or negatively skewed? Guys, what do you think? Is it positively skewed or negatively skewed?
Positive.
Positively skewed. Why do we use this QQ norm for?
For plotting the data on the graph.
What do we check by using QQ norm?
Outliers or quartiles.
We check the normality of the data, whether the data is following normality or not. QQ plot. Let's first check it for the input variable x with the reference line. Do you think the data is following normality? How much of the data is falling exactly on the line? Very less data is falling exactly on the line, right? Even though in the IQR region, the data is little deviating from that line, reference line. So we cannot really say that the data is following normality. Let's check for the output variable, adipose tissue. How about this? This looks to be it's following normality, the adipose tissue, right? Well, most of the data within the IQR region is falling exactly on the line. There's a little deviation, that is still fine. Clear? Let's calculate the probability distribution. Histogram with probability equal to true. So it gives us probability distribution. So where do we have? They have the density on the column. This is a probability. So where do we have the highest number of data points? In which probabilities? Between 0.015 and 0.25 or 0.30. That's where we have most of the data is lying. The lines to get the distribution are just equal. You see here, if the data would have been following this dotted line, then you can call them as normally distributed, more or less. It's a kind of average that goes through. But here, the data is little up and down. It's slightly left skewed. Let's plot this between scatter plot to bivariate analysis. So far, whatever we have seen till here is all about univariate analysis. Box plot to understand outliers. Yeah, need to perform all this one after the other. Now we are going to do the bivariate analysis. Which graph you are talking about, Anika? This is the one. Okay. There's nothing but the dotted line gives you kind of average that you get. More or less, if the data follows exactly somewhere this distribution, it tends to follow the normal distribution. Because this line is also like looks like the normal distribution. But here, the data is little deviating, slightly left skewed compared to the dotted line. Just to understand, this is a histogram, right? Just to understand the distribution of the data, shape of it. Now, as part of bivariate analysis, the syntax is plot of x comma y. Now, what do you think? How the data? What kind of relationship do you think that exists between the x variable, which is waist circumference, and the y variable, which is adipose tissue? Guys, can you please comment on this? What kind of relationship do you think?
What cause for perfect positive?
Do you think it's perfect positive correlation?
No, it's tending towards
Okay.
positive.
So first of all, coming to the direction, there a positive relationship or negative relationship?
Positive.
There is a positive relationship because when the x is increasing, y is also increasing. So that means that is a positive relationship. So how strong the relationship is? Looks like it is not that perfect positive because the spread is increasing as you move forward, right? If the spread is maintained in the same way as it is there in the initial, then you would have called that as kind of more of a strong positive relationship. However, just by looking at the scatter plot, we will not be able to comment on the strength of the relationship. What is that we need to see to bring the objectivity to the scatter plot, the relationship? What do we need to see, friends? Correlation coefficient, right? A simple syntax to build this is plot of x comma y, but you don't get all these colors and name of the chart and all those things. Okay. Now I'm attaching this and building a correlation matrix between x comma y. So what is the correlation that you have? Point. What is the correlation coefficient? Small r looks like this 0.82 almost. So is it strong correlation or moderate correlation?
Strong.
If it is more than point, if the modulus of r is more than 0.85, only then we call that as a strong correlation, strong relationship. If it is between 0.5 and 0.85, we call that as moderate correlation, positive moderate correlation, right? This is perfectly fine. So your waist has got a kind of good correlation with adipose tissue. Both are having a relationship. So hence you can make use of this for your predictions. Pay attention here, friends. The syntax for building linear regression model in R is LM. LM for linear model. Syntax is lm of y tilde x comma data is wc comma 80. That is obvious that you need to provide. But the syntax is y tilde x. Dependent variable tilde independent variable. So now I'm building this linear regression model and capturing the result into a variable called reg. Let's build this. Y is the adipose tissue, X is the waist. Now let us see the summary of this result, summary of reg. Pay attention here, friends. So this is nothing but the formula we have used, lm of y tilde x. That's okay. Residuals, I'll come back to that. Let's look at the coefficients. What are the coefficients in the equation, linear regression equation? In the equation that we have used, how many input variables we have? And how many independent variables we have in our problem? Only one. Nothing but y is equal to beta naught plus beta 1 x. So this must be your equation. Y is nothing but adipose tissue is equal to, what is beta naught value? Here you are seeing the coefficient values are given, intercept value and coefficient of waist. These are nothing but, intercept is nothing but beta naught. So this is nothing but minus 215.98 plus 3.46 into x is nothing but what is x, friends, in our equation?
Is
Waist circumference, right? Clear? And this is the equation that we have built. But can we consider these beta naught and beta 1 values? Because in this overall equation, this beta naught and beta 1 are very, very crucial for your success of your prediction. For the success of your prediction. Hence, we need to be sure about whether we can consider these values in the equation that we are building or not. The check that we need to do is, if the intercept and waist values, intercept and beta naught and beta 1 coefficient values are nothing but these are the coefficient values. If the coefficient values are significant or not, can we consider them or not, is based on the probability value. If the probability of each of these coefficients is less than 0.05, what is this 0.05, friends? This is nothing but alpha value. And alpha is 0.05. So what is the confidence level at which you are predicting?
5%.
So,
5.
and alpha is 0.05. What is the confidence level at which you are predicting? 95, right? And alpha is 0.05. 1 minus alpha is 0.95. Clear? And the probability is less than alpha. Alpha is nothing but chance of going wrong. If your probability value, if it is less than alpha value, that means you can comfortably consider these coefficient values in your equation. Means they are significant. All your coefficients are significant. Am I clear with the point, friends? That is the first check that we need to perform whenever we build the equation. Okay. So once we check the coefficient level significance, then we need to see the entire model level significance by looking at this p-value. Even the entire model also should be significant. Even this value also should be significant. So by looking at this value, can you tell me whether this is significant or not? Is that significant, friends? What is this 2.2 into e power minus 16 means? This is nothing but 2.2 into 10 power minus 16. So if you expand this, how does it look like? 0.15 zeros. 2, 3, 4, 5, 6, 7, 8, 9, 10. The 16th position, you will get this 2.222. So is this less than alpha or more than alpha? What do you think, friends? Is it less than alpha or more than alpha?
Yes.
That's right. So that means the entire model is also significant. So once we have checked the coefficient level significance and the model level significance, that's when we look at the measure called multiple R squared value. Multiple R squared value means 0.67. This multiple R squared value talks about the percentage of the data points that are falling on the best fit line that you have chosen for your prediction. So this is the line that you have chosen. So with this line, only 67% of the data points, the actual data points, are falling on the predicted line that you are coming out with. And these are the predicted values, right? So is that accuracy is good enough for you? For your prediction? Friends? Is that 67% is good enough? Obviously not, right? And these are nothing but the residuals, nothing but the errors. Residual distributions, kind of box plot, quantiles. First quartile, third quartile, yeah, quartiles. Am I clear, friends? Standard error of residuals is also given, along with the degrees of freedom. Why it is 107, the degrees of freedom here? In the original number, what is the number of observations that we have loaded? 109. So your sample size n equal to 109. Out of it, take out both adipose tissue. So how many variables you have? 2. So that's why it has become 107. N minus 2. Clear? Am I clear, friends, with respect to how exactly you read the output of linear regression model? Okay. Just give me a second, friends. Okay. Sorry about that, friends. So are we clear? This is the data of overall 109 observations that we have used. So how do you improve the model's accuracy? Right? But any which ways, we cannot give the predictions as a single value. That's why we need to go with the confidence interval. I'm creating this confidence interval for the predictions. So REG is the variable in which we have saved the linear regression model output. I'm building a confidence interval for predicting the output of this with a confidence level of 95%. So with this confidence level, with 95% confidence level, the area under the curve that you need to cover is 97.5, and the possibility to go wrong is 2.5. This is a lower bound value and this is the upper bound value. So now you have got another 2 sets of coefficient values. If you make use of this value for beta naught and this value for beta 1, you will get the lower bound value in your range that you are predicting, right? And if you make use of these values, you get the upper bound value. Now, let's use prediction interval. Interval equal to predict. Now, if we convert this into a data frame and keep it in the thread, let's see what are the values we predicted. These are the predicted values. These are the predicted values. There's a lower range and upper range. If you see here, the predicted values are always having the wider range compared to even the confidence interval. Am I clear now? If you look at these numbers, the lower range and upper bound values in the range, your prediction interval is much wider than your confidence interval. If you see the correlation between the predicted values and the actual values, but what is the expected correlation, friends, between these two? The predicted values and actual values. What is the expected? What is the best correlation that you can have between the predicted values and the actual values of a variable? Guys, are you there? What is the expected correlation that you can have between the actual values and the predicted values? It should be one, right? It like if your predictions are very much accurate, they should be same as your original values, the actual values. So the correlation of a variable with itself is always 1. Now let us see. So there is only 81% relationship. These are. So that means our predictions are accurate to this level. Now, it's not only the accuracy that we need to look, we also need to look at the residuals, errors. Now, this is nothing but, what are we doing here? I'm taking the residuals from the REG and I'm squaring the residuals into residuals. I'm squaring the residuals, taking a mean of it and applying a square root. So that means, what am I doing? Residuals are nothing but the errors. I'm squaring the errors. So this is nothing but squared errors. And then applying the mean of it, mean on it. This is mean squared error. And applying a square root on that. So this becomes RMSE, which is a measure of error that you take into consideration for comparing the performance of the models. This is the first model you built. You got an R squared value and you have an RMSE value. Okay. So this R squared value and RMSE values will be useful for comparing the performance of the models with other flavors of model that you're going to build, right? Now let us see how much error we got. With square, impact of error will increase. No. The reason why we are taking a square on the errors, because sometimes these errors would be negative, right? Error is nothing but the actual value minus predicted value. If your actual value is lesser than predicted value, then the result that you are going to get is negative. That's why the square is applied to convert these negative values into positives. Then taking a mean of it, because it is always against the number of observations. Then applying the square root, so that this is one of the best reliable measure that you can make use of to compare the errors. Okay. Yeah, we will see more of the error measures when we get into the forecasting discussion. Okay. Fine. And now, so what is the difference? Now I'm building another model. What am I doing here, friends? While building a new model, what am I doing? What is the original syntax? In the first model, we have taken lm of y tilde x. But instead of x, now I'm taking lm of y tilde square root of x. Because we know that the input data is not normally distributed. If the data is not normally distributed, then we can make use of the transformation techniques to convert this non-normal data into normal data. And that's why we try with the different transformation techniques to make sure which one is giving the best result. Am I clear? The process of applying these mathematical formulas of a particular variable is called as transformation. It's called data transformation. So let's build this model, applying the square root on the input variable. Now let's see how the result looks like. Do you see any improvement in the accuracy of this model, friends? What is the first thing that we need to check? Guys, come on. What is the first check that we need to? Yeah, whether the coefficients are significant or not. So the coefficients both are significant or not? Both are significant, right? They are less than, probability value is less than alpha, 0.05. And that's why these 3 stars are given next to each. When 3 stars are given, that is pretty much close to 0. Okay? It is obviously less than your alpha value. So you can consider these two values for your coefficients. Then what is the next check that we need to perform? The overall probability, right? The model level probability. So is this significant? Guys, how about others? Only Hanika is responding. Others, are you clear about the concept or not? Others? Okay. And please respond, guys. I'm not actually taking this session for someone else. It's only for you. Okay. So the next check that we need to perform is the overall p-value, model level p-value. And this is also proved to be significant. Now, let's look at the accuracy of the model. So do you see any improvement from the previous version of the model that we built in the R squared value? What was the previous R squared value we got? 0.67. Now it is 0.6737. There is a slight improvement, but there is not much. Okay. So the transformation technique that we have used is not very helpful. So calculate the confidence interval, same syntax, predicted interval. It's fine. Okay. And now preparing the third model, building the third model. This time I'm applying logarithmic on the waste value input. Let's apply this. Let's see the summary of this. So is there an improvement in the model accuracy R squared value? It's almost same, right? But there's a slight 6753. It's more or less the same. And the coefficients are significant. Everything else looks fine, but the model's accuracy is not that better. Okay. So now, this time, instead of applying log on the x variable, I'm applying it on the y variable. So my equation is lm of log of y tilde x. Log of y tilde x plus x square. This is called polynomial degrees, polynomial transformation. X plus x square plus x cube and so on. This is waste into waste square. Okay, I'm applying log on the y variable, and on the x I'm applying the polynomial transformation. X instead of x I'm taking x plus x square. Okay, so now let us see how it works. Summary. Do you see any improvement, guys? Yes, right? It has come to almost 78%. Okay. This is how you can improve the accuracy of the models. Finally, let us try this. Applying square root on the y variable. I mean, this is not that good, but better than the previous ones. It is only 71%. Right? So this is how, unless and until you experiment with the data that you are handling, no one can say which model would be the best. It's purely experimentation based. Am I clear, friends? So you need to capture the R squared value and RMSE value for each of these models that you build. By comparing these R squared value and RMSE values, you need to take a final decision which model is better. If we have standard format, what to use? What do you mean by standard format, Anika? I'm slowly introducing the concepts to you guys. I'm not introducing all at one shot. Okay. So for predicting these regression outputs, predicting the y variable, which is a continuous data. So what are all algorithms that are available, and how do you make sure you get the best accuracy by using these algorithms while building the model, right? Only based on the experimenting, there is not square root or log. You can try with exponential, you can try with x plus x square plus x3, x cube, or instead of x, you can take 2x. Okay, anything. Unless and until you try it, you will not know. But it's very difficult to actually try out with all these transformations. That is where I asked you guys to spend some time reading about Box-Cox transformation and Janssen transformation. What they help you is basically what kind of transformation would be a kind of ideal for a variable taken into consideration, so that you can straight away start doing. You can take that type of transformations into consideration for performing the experiment. Okay. Am I clear, friends? Any more questions? Okay, fine. Let us look at the Python part of it. Python need to import these libraries, pandas, numpy, matplotlib for basic visualization. And I'm making use of same data. I'm loading the same data. WC80 is the variable. WC80.columns is waist and adipose tissue. Histogram to see the distribution of the data. And box plot to understand if at all there are any outliers. Right? And similarly on the output variable, dependent variable. Box plot. Drawing a plot between x comma y is scatter plot. Right? The same thing what we had seen. Bring the objectivity, calculate the correlation. 81.8. Now, to build the linear regression model, you need to import from the stats models library, you need to import the module called SMF. The formula API is the submodule that you need to import. So to build the model, the syntax is model equal to smf.ols of y tilde x dot fit. And to get the parameters, what are the parameters, friends? Yeah, coefficients. Parameters are nothing but the coefficients. Get the parameters, the syntax is the variable into which you have stored the model result dot params. Params is the short name for parameters. So you get beta naught and beta 1 values. And if you do model dot summary, then you get the complete output. Just pay attention here. This is a OLS regression model results. Dependent variable, y variable is adipose tissue. And the method that is used is ordinary least square technique. And R squared value, adjusted R squared value, we will see what is the difference between R squared and adjusted R squared in multiple regression, multiple linear regression. Okay, what is the overall probability value? And alongside of it, we are also given the AIC values and BAC values in the Python. AIC stands for Archaic Information Criteria. Archaic, AC, K, Archaic Information Criteria. BAC stands for Bayesian Information Criteria. So whenever you are comparing multiple models, that's when these measures will be handy. Whichever the model has got the least AIC and BAC values, and those models tend to give the best performance. So for selecting a model out of the stack of models, that's where these values will be really useful, AIC value and BAC value. And the coefficient values, their significance through the probability value, right? So this is how you need to read the output of Python models. Now the experimentation remains same in both R and Python. You need to try with different. So to get the confidence into the predictions based on confidence interval, this is the syntax: model dot conf underscore int. I'm just printing that. You'll get this. Just give me a second. Printing this. So these are lower bound coefficients for lower bound value, coefficients for upper bound value. Predictions based on predicted interval, prediction interval. Now, to build the basic visualization plot, matplotlib, under that pyplot we need the scatter diagram, right? The scatter diagram along with the best fit line. The correlation value. And similarly, build different type of models. Y tilde log of x. Before log, why am I using NP? What is NP here, friends? NP is nothing but numpy. Okay. So you can build the model too and see the output of it. Model.summary. You can see what is the accuracy. R squared value, not much improvement, 675. Right? The syntax is this. I don't think we really need to go through each and every line because it's the same steps. What we're going to do is what we are already seen, right? Any doubts, friends? Any questions on the simple linear regression in R, Python, anything? Any questions? Yeah, that's right, Hanika. So please complete the assignments and start practicing. Only then you will be able to get hold of what we are discussing. Otherwise, if you get a huge gap after we discussing these topics, you tend to forget the most important points that we discussed. Right? Please practice. Okay. So with that, we are done with simple linear regression. Now we'll discuss about multiple linear regression. But before that, just a small break of 2 minutes. Yeah, I'll be right back. Okay, friends, let's discuss then. Python code or R code will be shared for reference. Yeah, I think the codes will be shared in your LMS. If not, then probably you can go through these recordings. Because if you are given the code blocks, we don't entertain of giving this. The reason being, you just execute straight away. So you don't get a hold of writing this right from scratch. Better you write it right from the scratch. Okay, that's what we prefer, so that you will be used to it. I think they're already shared, I think, if I'm not wrong.
Yes, they are. I think in the file.
Okay. Okay, fine, guys. Now let's move forward. So when y is continuous and x is a single input variable, irrespective of whether it is continuous or discrete, then we had gone for simple linear regression. What is multiple linear regression? Only the number of input variables is the difference between simple linear regression and multiple linear regression. Multiple input variables could be continuous, could be discrete. Both the cases we can go for multiple linear regression in terms of predicting the y variable, which is continuous. But if you have the discrete data, you need to convert them into the dummy variable. You already seen, right, how to convert the categorical data into dummy variables. And this is the right way of converting into the dummy variables. Let's say if you have 4 variables like petrol, diesel, CNG, a variable called make of car of 4 classes: petrol, diesel, CNG, LPG. That's the right way of converting them into having a dummy variable for each of the class and represent whichever the record has got that value as 1, otherwise 0. This is the right way of representing. Now, please could you go through this case study? This is what we are going to solve now for the multiple linear regression. Just go through it for a second. So this data set is all about the cars data set. It has got 81 observations in it. So in this, we have overall 5 variables: volume, horsepower, mileage per gallon, speed, and weight. Right? So we need to predict the mileage per gallon, the mileage of a vehicle, given the other 4 details. So we need to predict an equation. We need to come out with an equation to predict this mileage based on the other 4 input variables. Okay. Now let's look at the data. By looking at this, what is the output variable, friends? What is the y variable? Guys, come on. What is the output variable? Why is it so stubborn? MPG, right? So MPG is the output variable by X1. We have multiple input variables, right? X2, X3, and X4. So what is the type of our output variable? What is the data type?
Continuous.
Continuous. How about the input variable?
Continuous and discrete.
Which one you are seeing as discrete? So they are all continuous, right? See, this horsepower, you can still represent in 49 or 49.0. That still makes sense. Similarly, volume as well. So they're all continuous, right? Let me just refresh this so that. Guys, this is the most important slide. Though you are predicting, or your predictions look somewhat reasonable, it is not just good enough. We need to make sure all these assumptions are satisfied. Only then the model that you are selecting can be finalized for further consideration of either moving it to production or considering as the best model, right? What are these assumptions? These assumptions make sure that the model which you are selecting would be able to work even for the unseen data very well in future. Okay, let's first understand the assumptions first. These assumptions are categorized into 4 classes. One is assumptions about the parameters. Second one is assumptions about the errors. Third one is assumptions about the predictors. What are the predictors, friends? What are predictors? Predictors are nothing but the input variables, x1, x2, x3, and so on. No. Predictors are the variables that you use to predict the output variable. They are the input variables or independent variables. Now, the fourth set of assumptions is about the observations. What are the observations?
Predicted value.
Yeah, the actual values given in your data. Okay, and that is why. And let's first see about the parameters. What are the parameters? Coefficients, right? It is not just good enough that your input variables maintain a linearity relationship with the output variable y. Even your predictors, all of your predictors should maintain, all of your parameters should maintain a linear relationship with y. Only then your output, the predicted values that you come out for the output would be much more sensible. That is about the linearity assumption. The second one is assumptions about the errors. This is the most important section. So what are the properties that errors needs to follow? They need to follow IID properties. IID is nothing but independent and identically distributed. What do you mean by independent? If you plot these residuals, errors, they should be independent of each other. That means error of or the residual of one observation should not impact the outcome of other observations error. It should be randomly distributed like this. Should be independently distributed. Otherwise, if you have something like this, but here what is happening? They are following these errors or the residuals are following a pattern, right? So the errors or the residuals that you are plotting should not follow any kind of patterns. They should be randomly distributed or independently distributed. There should not be any sort of relationship between the errors of different observations. Am I clear with that point? Online folks? Okay. And the second part of it, independent and identically distributed. What do you mean by identically distributed? Number of data points that are above this mean zero line should be the same as the number of data points that are on the other side of the line. That means identically distributed, symmetric distribution. Right? And the second property is about the mean of the errors should be zero, which is very much known thing. And third thing, which is the most important behavior that you should see when you plot these errors, you should have a constant variance. What do we mean by constant variance? Let's say if you are plotting the errors, if they look like this, what are you observing here? The variance remains constant throughout. Variance is nothing but the spread of the data, right? So the spread of the data at the starting looks to be same even at the end, even at towards the end. So that means the variance is constant. When the variance is constant, that is an expected behavior when you plot the errors. If the variance among these errors is constant, then you call that property as homoscedasticity. We call this property as homoscedasticity. But otherwise, if the variance is not constant or not consistent, let's say if the variance looks like this, right? Here in the starting, the variance is very less. But as you move forward on the x-axis, the variance keeps increasing. Here you have maximum variance, right? That means your variance is not constant across. This is not an expected behavior. And this kind of behavior is called heteroscedasticity. If the variance is constant, you call that as homoscedasticity. If the variance is not constant, you call that as heteroscedasticity. If the variance is not constant, then that is a problem that you need to deal with. Then how do you deal with this? You built a model, you get to see the residuals that you are calculating, which are nothing but the difference between actual values and predicted values. The residuals that you are calculating are not constant, are not maintaining a constant variance. Then how do you deal with such kind of problems? Any idea, friends? What kind of techniques you can use to deal with this heteroscedasticity problem? Guys, what techniques do you use to solve the heteroscedasticity problem? Making it in similar unit? Not exactly. So even the transformation would really help you even to solve these kind of problems. You transform the data. Instead of x1, you take log of x or x1 square. Depends whichever is giving the best result. You need to stick to that type of transformation, right? Heteroscedasticity is the problem that you have in your data. Homoscedasticity is a kind of expected behavior that you would like to see, right? And the last but not the least assumption about the errors is independent of each other. What should be the independent? These errors should be independent of each other. If they are not independent, that means if they are maintaining a sort of dependency among themselves, then it is called as an autocorrelation problem. This is also a problem, friends. Each observation's errors should be independent. If they're not independent, if they are maintaining any dependency across the observations, then that is a problem that you need to deal with. That's called as autocorrelation. How do you deal with this autocorrelation? They should be independent. If there is a dependency, then we will see in time series how do we deal with autocorrelation problem. Autocorrelation means maintaining correlation with itself. But is it with the same level of lag of values? That's what we're going to see. Okay. Now, the third thing is about the assumptions about the predictors. What are the predictors? X1, X2, X3, and so on. They should be non-random. Means you should select all relevant variables into your equation to predict the output variable. There's no point in selecting more and more variables that are available for you, though they are not relevant. Okay. And they should be measured without any error. Your input values, the x1 value, x2 value, and so on, all these should be measured without any error in terms of measuring that. Right? The next one is they should be linearly independent of each other. If not, if they are not linearly independent, means they should maintain a linearity relationship with the output variable. But at the same time, while each of these input variable maintain a linearity relationship with the output variable y, they need to be independent. Means there should not be any relationship between the two independent variables or two input variables. If not, if they are getting into relationship, that's why it is called the collinearity problem. If there is a collinearity problem existing, that means you would need to drop off one of the variable which is not helping you in the better prediction of output variable y. You need to drop off one of those input variables which are getting into the correlation, right? So this is called collinearity. Now the last but not the least assumption is about the observations. These observations are nothing but rows, the actual values that are given. They should be equally reliable. That means they should be captured without any error. So that's where your quality of the input is highly important, because your output that the algorithms are going to suggest are purely going to be the quality of the input that you are giving. If your input is highly qualitative, your outputs are also qualitative. Hence, make sure you understand your business problems right and collect your data without any errors. Okay, these are about the assumptions that your regression model needs to satisfy even before you call that model as the best performing model. Am I clear? Any questions, friends? Any questions you have on this particular slide? It's the most important slide. Any which ways, yeah, I'm going to repeat this in tomorrow's session as well, at the first thing. Then we will move forward with the multiple linear regression model building. Clear, friends? So any questions, I can take it up. Tomorrow we'll have a classroom. I'll be there in the classroom available. So whichever the mode you prefer to attend, you can attend through that mode. Clear, guys? Any questions? Okay, guys. Thanks for attending then. If you don't have any questions, just give me a second. Okay. So thanks for attending. We'll meet tomorrow. Okay. Bye-bye.